So for me, mine planning is a broken model. I think it has been the whole time I've been in the mine planning world. And that's the title of the presentation. And so I don't just want to talk about the problems. I do actually want to sort of, talk about some potential solutions as well. Okay, here we go. Finally, a lag on the slide change. I've always loved the saying that everyone has a plan until they get punched in the mouth. Being a planner, I've always sort of liked that saying. And when I think about the mining industry, I think that there's a misguided belief out there, particularly from people who aren't mine planners or don't have a mine planning background, that that mine planning has some high degree of science behind it, highly reliable and should be trusted upon. After 30 years in the industry, I don't necessarily think that's the case from my experience. And so I take the approach that if I've got to put some home truths out there and they serve to be that punch in the mouth that sort of wakes the mining industry up a little bit, that's really to some extent what I'm about. So just a bit about me and who you're listening to. I'm an Australian mining engineer. I've worked in the Australian mining industry for about 30 years or so, but only ever in open cut. I haven't been underground at all. And so all of my examples, stories, etc., and my discussion relate to my background in open cut. But I know enough about underground to know that I think it pretty well crosses over into the underground area as well. I spent 10 years with Rio and Thiess contractors and pretty much followed the generic sort of mining engineering path of carrying out a number of technical roles of drill and blast design, etc., before moving into scheduling, then moving over to the iron ore and spending some time as a grade control superintendent and production superintendent before coming back to coal as a tech services manager or a mine planning manager, they're often called. In 1999, after 13 years in the industry, I decided it was time for a change and I founded my own mining consultancy. And I grew that to about 30 people or so before, in 2012, I decided it was time for a change again and I sold my mining consultancy. I was a bit jaded with the industry at the time. I was a bit jaded with the, almost like the arrogancy of mining engineering and everyone sort of knew everything and you couldn't tell anyone anything and so on. So I left the industry for a few years and bought a locksmith business that I still own today. But after about 3 years in the industry, spent wondering, should I let that 25 years of knowledge disappear, never to be seen again? I decided that in the scheme of things, that wasn't really a very clear idea. And I should just keep my hand in. So in 2016, I started back just doing some occasional consulting in the industry again. In 2020, I came to the point where I guess I was sick of the mining industry meeting the definition of insanity, certainly in the mine planning space, in terms of just continuing to do the same thing over and over and expecting a different result. And I decided that was time to do something about that. And so for me personally, I came to the point where I wanted to work more on the industry rather than working in the industry. And so I unashamedly borrowed the legacy of the New Zealand All Blacks, who had this awesome winning culture. And their legacy is that they will leave the All Blacks jersey in a better place than they found it. And so I came to the conclusion that in actual fact, I wanted to leave mine planning in a better place than I found it 30 years ago when I started. And at this point in time, I certainly don't believe it is in a better place than I found it 30 years ago. So the first step in that journey for me was writing a book. That was a big step for me because I'm an engineer. Give me a spreadsheet anytime. I hate writing and I certainly hate writing books. And it took me about 14 months or so. It was a journey. It wasn't a journey that I loved in any way, but I think that it has gone very well and has certainly helped. And I think it's helped towards the purpose of leaving mine planning in a better place than I found it. Now, I guess I do want to say one thing, and that is I don't consider myself an industry expert. I just happen to have worked in the industry for 30 years. I love mine planning and I care about it a lot. I love challenging paradigms. I love asking why, but I haven't gone off and done a big academic study or anything like that. So I'm really more talking from experience rather than study. So I found this quote a while back, in that trying to predict the future is like driving down a country road at night with no lights while looking out the back window. And I think that is particularly relevant because that's actually how I think of mine planning to some extent. We call it mine planning, but really when you think about it, in creating mine plans, we're trying to predict the future. And we do that while we are looking out the back window. And in terms of that looking out the back window, we collect an enormous amount of data from equipment management systems and other reporting systems on site. And then we spend many man-hours analysing that data, and we arrive at comprehensive time usage models that build up the production time that we can expect from equipment, and also historical production rates. And so therefore what sort of productivities we should assume going forwards. And we carry out all that analysis and effort to arrive at a single sort of snapshot for every piece of equipment at a mine site that has assumed production and assumed production levels and equipment hours. And so, you know, we are looking out the back window to endeavour to predict the future. But there are some things that are missing in the mine planning world. And for me, the key missing ingredient starts with variability. And I really just want to take variability and talk about it a bit more, just through sort of one example in the scheme of things. And so if we talk about truck shovel operations and the variability that exists within truck shovel operations, firstly, in terms of the production hours, there are a whole pile of lost time events that are related to the activity that's being carried out that occur, and every one of them is variable. And so they are things such as unscheduled maintenance, waiting on various equipment or blasts to happen or access, dust delays, the shovel hang time while it's waiting for trucks to load, the trucks queuing themselves, shovels or excavators positioning, deadheading, parking up because there's nothing to do. And then in addition to that, we have a whole time of lost time events, a whole spectrum of lost time events that are not related to the activity. They occur regardless of which block of dirt is being sort of excavated where. So they're things such as meal breaks, shift change, scheduled maintenance, refueling, sort of toolbox talks, weather, and so on. And again, that's just a subset of lost time events. So we've got a whole pile of lost time delays. And then in addition to that, we have other areas of variability. So the actual dig volume is going to be different to the design. The material density is going to vary. Every shovel bucket is going to have a different payload. Every truck is going to carry a different payload. All the elements of the truck cycle time are variable for every load. The number of operating trucks throughout a shift will vary on a constant basis. We have things such as the face height and face width that the excavator is digging will vary. That will change the productivity of the digger. You know, whether the blast itself was a good blast and is well fragmented, or whether it's poorly fragmented is going to have a significant impact on the digger productivity. And then there's even different dig methods, such as whether we single side or double side load or top loading and so on. So, you know, that's a list of some of the variabilities in truck shovel operations. It's a reasonable length list, but in actual fact, it's really just a subset of the variabilities within a truck shovel operation. There are so many more variables than that. And, you know, that variability occurs within every other process within mining. So we get the same sort of variability issues that occur within drilling, blasting, dragline operations, processing the ore, railing, shipping, etc. And so, you know, for me, if we think we can take everything that happens out there, all of that variability, and boil that down to a single snapshot in time that we then set out to hold the production team accountable to execute, or we report a number to the stock market, or whatever it is. Everything that we do is sort of single point numbers. You know, for me personally, I think we're kidding ourselves. We're living in a fantasy world if we think that we can just work on a deterministic basis and report single point numbers. I want to talk about variability a bit more. Again, just using a sort of a fairly simple example. And so in this simple example, we've got 6 steps that happen in sequence, where we drill first and then we blast, we mine the waste and then we mine the ore, we process the ore and then we rail it. And this is a balanced system in this example. So each of those tasks takes 10 days, is our sort of planned production. And so therefore, overall, that will take 60 days as the plan. You know, but we know that we have variability within each of those tasks. And so if we assume that each of those tasks has a standard deviation that's about 30% of the mean time, each of those tasks has a standard deviation of about 3 days or so. And in terms of coming up with that 30%, I actually did a bit of work collecting production data from equipment and so on, and typically found that the standard deviations were around 30 to 40% of the mean sort of. So I've tried to keep it somewhat realistic in the scheme of things. So yeah, having that set of standard deviations across each of those activities means that sure, the mean time is 60 days, but in actual fact, it could be anywhere between 40 and 80 days to carry out those 6 steps in that sequence. And you know, if we actually put some numbers behind them from a normal distribution point of view, we're a 41% probability that we will be out by 10% in our plan. And we're a 17% probability that we're going to be out by more than 10 days. So, you know, it is crazy for us to just expect 60 days and to hold people accountable to that and so on. But it gets worse than that, because those calculations are based on the assumption that it's a normal distribution. And in the mining industry, distributions are rarely normal. They're typically skewed. And so what I've got here is I have a plot of actual dragline daily production volumes for a year, which is the blue line, varying between 0 BCMs a day up to about 60,000 or so. And just for comparative purposes, I've plotted on a normal distribution that's in the red line. And so you can see it's very much skewed to the left. And one of the things that happens in the mining world is that we operate in a world of asymmetrical outcomes. So, you know, it's very rare that the upside is going to be as significant as the downside. You know, for this dragline, we're probably going to plan it somewhere around about 40,000 cubic meters a day is what we're going to plan to move. You know, you can see there that there's not a lot of upside on that. We tend to plan what we actually think the machine can achieve with, you know, nothing going wrong, the operator's having a good day, the blast as well, the shot is well blasted and so on. So we always tend to plan at the best, but the reality is that there's a whole pile of things that are going to cause that machine to achieve less than planned. So that was sort of some discussion on variabilities, and you know, the next thing that very much sort of relates to that is dependencies, and we sort of ignore variability and we also ignore dependencies, and I think that creates a lot of grief in the scheme of things. And so I want to talk about actually. One of the things that happens through dependencies is that any losses in time are actually carried through the system. Any gains that we make in time are lost as they progress through the system. Again, same story. I'm going to give a fairly simple example to sort of explain it. So in this example, we've got an excavator that we're planning for it to dig block B. But before we can start block B, there are 2 tasks that have to happen. And I've assumed that those tasks are normally distributed. And so the first task that has to happen is that the excavator that we're planning to dig block B has to actually finish digging block A first. So that's a resource dependency. We need that resource to finish somewhere else before we can start this task. And also, before the excavator can start on block B, the blast crew has to have blasted block B. So a task dependency, there's a previous task that has to have happened beforehand. Now, as I said, I'm assuming that those two tasks in terms of the excavator digging block A and the blast crew blasting block B are normally distributed. So therefore, they're 50% likelihood of falling either side of the mean. The one thing that's going to happen is that they're not going to fall on the mean. They're going to finish either side. It might be 1 minute late or 1 minute early, or it might be 5 days late or 5 days early. But each of the tasks are going to finish early or late. So then we have 4 possible scenarios happen. And so the green box denotes when the task finishes early versus the red cross is when it finishes late. So in our first scenario, our blast crew are running late, blasting block B, but our excavator is ahead of plan on block A. So the excavator's finished early, but the blast hasn't been fired. So therefore, we can't start early. We're going to finish up starting late. We're going to start that when the blast actually goes. So therefore, starting block B in scenario 1 is going to start late. We've got the second possibility is where the blast crew finish early and the digging of block A finish early. And so in actual fact, in that scenario, we can start block B early. Third scenario is where the blast crew finish early, but the digging of block A by the excavator runs late. And so therefore we're going to start late. And then the scenario 4 where they both run late. So out of the 4 possible combinations that could occur in the scenario where there's a 50% chance of finishing early or a 50% chance of finishing late for each of them, basically we are only a 25% chance of starting block B early, and we're a 75% chance of starting block B late. But again, it gets worse. Everything gets worse. There's one thing you'll find about this presentation. It's always downside. There's more downside than upside. So, that's when the task is dependent on 2 prior tasks in terms of digging and blasting. But what if it's dependent on 3 prior tasks instead, or 4? So, in addition to having the excavator having finished digging block A and we've blasted block B, we need to have installed a sump, or we need to have put a ramp in, or we need to have dewatered an area, or one of the many other things that occur in the mining sequence. So in that scenario now, where we are dependent on 3 prior tasks instead of 2, the probability of starting block B excavation early is now decreased from 25% to only 11%. And there's more. So, in that example, it was based around 50% probability of finishing early or a 50% probability of finishing late, which means that we've planned at P50 for our input assumptions. Unfortunately, that doesn't tend to happen. Plans always have stretch targets built into them. So it's more likely that we're planning at a P40 or something instead of a P50. So we now only have a 40% chance of finishing early, but a 60% chance of finishing late across those 2 dependent activities. So in that scenario, again, now instead of a 25% chance of starting block B early, we now only have a 16% chance. And if we're planning at P30 instead of P40 or P50, we're now down to only a 9% chance of finishing that block early. So from there, I went into a bit of an exercise following a discussion I had with a colleague, and it was about whether P50 in equals P50 out. And by P50 in and P50 out, I mean that P50 in is that all of our input assumptions into the plan have a 50% probability of being the right number. And P50 out is the outcomes from the plan. So whatever that is, whether that's tons mined or, being in a certain position, certain face position at a certain time, then the probability of achieving our outcomes in a P50 is there's a 50% chance of achieving those. And so, it would just seem logical, you would think, that if you planned with P50 input assumptions, that you would be a 50% chance of meeting your target outcomes. So what I did was I used a fairly simple probabilistic scheduling tool and set up a simple example, similar to the previous ones I've talked about, where there's sort of 6 steps in the sequence. And so we go from mining the coal in block E to washing block E, and then railing sort of block E. Each task takes 12 days in the sequence. Each task is dependent on a prior resource dependency and a task dependency. And each of the tasks has a 30% standard deviation that's 30% of the mean. So 3.6 days sort of standard deviation for each of these tasks. Now, what happens with dependencies is that we get what I've called slippage in the schedule. And so after running the simulation, this red bar indicates the actual simulated outcome versus the deterministic sort of schedule that we've based it on. And so that bar is the P50 output, P25 and P75 are the two ends of the sort of the red Gantt bar. So when we start with the first step in the sequence, which is drilling, which is not dependent on the area, any other steps in the area beforehand, then we have a 50% chance of finishing that on time, with again some still variability around when that will finish. But once we move to blast F, which requires the blast crew to have finished blasting block E, and it also requires the drill to have finished drilling block F, we now have some slippage in the schedule, which stems from the 25% probability of the gain being carried versus 75% probability of a loss being carried through. And so we now have a day and a half slippage in the predicted outcome of when that task will actually finish. And that slippage just continues to grow throughout the schedule. So you can see we've got 1.5 days blasting. Once we get to mining the waste, we're at 3.5 days slippage. Coal, mining the coal, we're at 6 days. Washing it, we're at 8 days. And by the time we get to the 6 steps in that sequence, we have 10 days slippage in total after the 6 steps that are in sequence. And that's a 10-day slippage in what is 6 activities of 12 days each. So we were predicting 72 days from the time we started drilling that block to the time we put it on a train, whereas we now are actually at 82 days instead of 72 days. And so that's a 14% sort of slippage in the schedule. And this is the P50 here and the P25 and the P75. And so you can see that our deterministic schedule actually only has a 2% probability of being right. We're only a 2% probability of finishing on time. So I just wanted to compare that back against when I first started speaking about variability. And I had that simple example earlier of the 6 tasks that took 10 days each. And so, you know, the mean deterministic time for that was 60 days. And then we had some variability around that 60 days. Whereas now, once we've introduced the dependencies into our scheduling, we now have a slippage of 10 days. And so our mean of 60 days that we're predicting from our deterministic schedule is actually now wrong. And from a probabilistic scheduling point of view, it's now 70 days instead of 60 days. So you can see that the time frame has slipped. And then we still have the variability around that 10-day slippage. So effectively, instead of being the normal distribution at 60 days, the normal distribution is now centered with a mean at 70 days with distribution around it. Excuse me, that's fine. But that was a simple example where we had no inventories or buffers. And the reality is that in the mining industry, we do build buffers into our schedules through inventory. So I then wanted to extend that example into, okay, fine, what if we introduce some buffers? And so what I've introduced into the schedule to rerun into this example is a 5-day task buffer where the activities themselves in terms of the resources are still working consistently. So the excavator that's digging block E finishes that waste and then goes straight onto block F and then goes straight onto block G. However, there's now a 5-day offset between when the blast is actually fired and when the equipment is scheduled to dig it. So we've introduced a 5-day buffer between activities. So in this case, what happens is we still get slippage and it still grows throughout the schedule, but it's reduced. It's not to the extent that it was previously in the example with no inventory. And so by the time we get to railing, we now have 4 days slippage instead of 10. So 4 days on a 72-day sequence is still about a 6% slippage, even though we've introduced 5 days worth of buffers. And we're now at a P29. We're at a 29% probability of finishing on time versus the 2% probability that we were without any inventories. So I ran that over a few different examples of length of buffers in terms of the inventory between tasks to just come to a conclusion about whether P50 in does equal P50 out. And so the first example was the 0 days inventories, and that was the 10-day slippage and the 2% probability. Then I showed the 5-day buffer with the 4-day slippage and a 29% probability. Now, even if we get to the point of 13 days buffer between each of those tasks, and bear in mind that each of those tasks are a 12-day task in this simple example. There are 12-day tasks with a 13-day buffer in between each of them. So the buffer is actually greater than the length of each task. Even in that scenario, we still get to the world where our P50 out is only 44%. So we're still getting slippage. There's still a day's worth of slippage, and our probability of achieving the outcomes is not the same as our input assumptions. So that's variability and task dependencies. The third sort of crime that I want to talk about in the scheme of mine planning is really what I think of as the worst kind of plan, which is an optimistic plan. And pretty much every plan that I see in the Australian mining industry, unfortunately, is an optimistic plan. So if we talk about optimistic plans, for me, I actually see them as an insidious disease within the industry. I think that they are something that there really needs to be something done about. When I think about my 30 years in the mining industry of mine planning, and when I started a long time ago, plans have always been optimistic, but I think they are now at the point where they are more optimistic than they have ever been. There is stretch. Stretch is just a term that is just built into every plan. And they actually, I see mine plans that are at a level of ridiculousness in the scheme of things. What's fairly common practice is that a mine planner, well, as I say, do a lot of work around creating the time usage model and historical productions, and we'll build the schedule. Because the mine planner has been sort of beat around the head a bit previously and knows that sending a conservative plan up the ladder is not going to be accepted. By default, the mine planner, I think in most circumstances, already actually starts with a little bit of optimism built into their plan, because they know that that's a minimum that's going to be required. And they really start off trying to get away with the minimum that they can to some extent. So what happens though is that plan is created, and it will head to site management, the GM or something like that, and invariably comes back with a no, the cost per tonne's too high, or there's not enough tonnes produced, we need a better plan. So the mine planner will go off and run a second version and put in some more optimistic assumptions, and typically get to the spot where they're creating something that may happen, but they're far from convinced that it's going to, and there's starts to become some doubt about whether it's actually an achievable plan. That heads up and it's approved by the site management level, then heads to an executive level within the organisation, and often comes back from the executives with no, I'm not reporting that to the market. I'm not giving that guidance. That is not consistent with our previous market guidance, etc. I want a better plan. And so it comes back to the mine planner, who now is at the point where they are going to produce something that they have zero faith in it working. Often it's actually something that to some extent they're almost embarrassed to own and put their name against, but it's come down from on high. Here's what we need. And so they build a set of assumptions in there that they don't typically believe are going to happen at all. And so I just sort of created this table to build on the sort of the case that I gave previously, where we talked about 2 tasks in sequence. And if it's normally distributed with a P50, then there's a 25% chance of finishing early. Now, if we take that and we extend that to 6 tasks in sequence instead of 2 tasks in sequence, and so that's more representative of drilling through to railing or shipping or whatever. And again, these examples ignore any inventories that might be built in. But when you take six tasks in sequence and you follow it through, then there's only a 2% chance of actually finishing ahead of plan. And so that really just is about that. Losses are carried through the system, but gains are not. So where are we from a mine planner's perspective at this point in time in terms of, I guess, what I've spoken about so far and those sort of three particular issues? So what happens is the mine planner is producing plans with optimistic inputs. And so they know their plan is wrong. They don't believe it in the scheme of things. Not only that, because of the tools that they have available at their fingertips, they're carrying out deterministic planning rather than probabilistic or stochastic scheduling. So they are carrying out a plan that has a whole pile of single point results and outcomes from it. And the fact is that they know variability is real. And so they know it's going to occur. And so that the plan is prone then to even further error in terms of it's deterministic and it's based on optimistic assumptions. So what do mine planners do then to cater for what I would call poor planning practices? And that's not necessarily reflective on the mine planners themselves. You know, they can only work with the tools that they have available. If there's no probabilistic scheduling tools available, then they don't have one of those to work with. And if optimistic assumptions are mandated, then that's what they have to work with. So, you know, what do they do to cater for those poor planning practices? Basically, there's two things that mine planners do. The first thing is they build an inventory, and they build it in everywhere. So if there are 7 steps in the sequence from drilling through to shipping, every one of those single steps has inventory built in front of it. And that inventory primarily has two purposes. It's there to ensure that resources continue to work and resources don't have downtime due to their next activity not being available to do. But also what it does is it hopefully extends what I call the shelf life of a mine plan. And so the shelf life of a mine plan for me is when the mine plan gets to the point where it's no longer relevant or applicable. So, you know, every mine plan starts out sort of somewhere close to the sort of the equipment being in the right face positions and so on. As the mine plan progresses, and particularly if it's optimistic and doesn't have variability built into it, then what happens is that the actual gets out from the plan. So face positions wrong, the predicted times for when resources are going to finish certain activities and start the next one becomes wrong, and it gets further out as the mine plan progresses until it actually gets to the point where it's so far out that it's reached its shelf life and it's actually no longer of any use, because you can't base any decisions on a mine plan that is a long way out from reality. So, you know, building inventories into a plan sort of extends the shelf life of a mine plan. Now, the other thing is that even though you build inventories into the schedule, invariably there's a pretty fair likelihood that at some point in time the plan is going to fall over, and as I say, it's reached its shelf life and it's no longer reasonable in the scheme of things. And so to cater for that, typically what you try and build into your plans is flexibility, and that occurs by actually having spare faces, and so that's spare working areas for equipment to go to, be it drills, you know, an area for them to go and drill, a face with blasted dirt for an excavator to go and dig at or whatever. And so building that flexibility in allows those on-the-fly decisions that happen when the mine plan has reached its shelf life. And so the production people and the planning people have gone, okay, we've got an issue. These two tasks are going to have an interaction. We won't be able to start the second task because the first task hasn't finished, or whatever the issue is, but we're going to have some form of interaction that means that our plan is now wrong and we need to change a plan. And so having a spare face allows you to carry out a change of plan on the fly without actually having to sit down and reschedule and resequence the whole lot. So flexibility is effectively our version of contingency planning. Now, the problem with that is that those two steps, those two solutions, both cost money, and they both cost an ordinary amount of money in terms of, you know, carrying inventory is money that you're spending earlier than you need to. And as I say, there's inventory carried in front of every step in the sequence. And so they're generally, most mine sites work with a significant amount of inventory. And then actually building in flexibility costs you as well. Spare faces, to create a spare face is you have excavated material earlier than you had to, and you've basically ultimately created a larger void. And so creating a larger void is digging dirt earlier than you have to. It results in longer haul distances and all sorts of other things. So those two solutions cost money. That's without even considering all the other inefficiencies that occur as a result of what I would call a poor mine plan. And so they are things like shortcuts. You know, it's common practice that, for example, we need that ore to go in this blend. Let's just dig half of the waste out the way, uncover the ore that we need, then let's go and grab that ore, and then we'll get back to the waste when we need to, sort of, and so on. You know, I've seen lots of times that the drill is only drilling half the width of the shot because the trucks have still got to run past on the other half of the shot, sort of, and so on. And you get all these inefficiencies that ultimately lower the productivity assumptions that you have made, that you have built into the plan. You know, if that shortcut was a better plan, then you would have done it in the first place. It wouldn't be a solution to the plan. And the other thing that happens is that you finish up moving equipment. You have an excavator that now the blast wasn't fired in time, so it's now got to walk to another area in the mine, to another blast. There's deadheading time that again was not built into your plan. So poor mine plans, what I would describe as poor mine plans anyway, that aren't representative of reality, do cost a lot of money. So what should we do differently? For me, it just starts with the headspace, the whole approach. You know, we need to think about things differently. We need to change our way of thinking. We have tools, etc. It doesn't start with the tools. For me, it actually starts with the way we approach things and the way we think about things. You know, and we can't fix the problem without recognizing that we have one in the first place. As I say, in my 30 years of mine scheduling, the approach to mine scheduling is basically still pretty much the same now, with just a different set of tools and a lot more complexity that we build into our plans and so on, because we have the IT capability to build complexity into our plans. But we pretty much still just take the same approach that we had for 30 years, except for that we're actually now more optimistic than we've ever been. And I actually would, I think we can actually go right back and just start at the terminology level. And instead of calling it a mine plan, because a mine plan involves, it implies some level of certainty. You know, people hear about a mine plan and they think that it's a scientific thing, that it's going to be accurate, it's going to be spot on, and that digger should be in that spot in 12 days' time, or we will get 10.1 million tons next year, etc. So the use of the terminology mine plan implies a level of certainty that I don't believe is there. And so maybe we should be honest and we should stop calling it a mine plan. Instead, we should call it a mine prediction or a mine forecast or something, which is actually real in terms of the fact that it is purely a prediction of the future. And so maybe we should start talking in ranges and risks and uncertainties rather than the deterministic mindset and approach that we take, where we talk about everything in concrete numbers like they are actually going to happen. So when it comes to the whole variability, etc., we are our own worst enemies in the mining industry. You know, our lack of consideration of variability and in fact, the minimal discussion that I typically come across about variability versus the loads of deterministic discussion that I come across instead is part of the problem. We drive a culture that increases variability. So, for example, rewarding record shift production. I've worked at mine sites where the dragline or the shovel has achieved a record shift volume-wise, beating a previous record from 5 years earlier or something. You know, and that's rewarded. It's acknowledged. The crew become superheroes on site. I've seen stickers produced that have the date and the shift and the crew and what the target, you know, what the actual was, sort of, and so on. But the interesting thing is that while there's a lot of hoo-ha about that record shift, what you never actually hear about is what was the volume mined the shift before or the shift after. because I think there's a pretty high likelihood that the shift following that record shift was going to be way below target in the scheme of things. And so rewarding and acknowledging record shifts or, these one-off peaks is only increasing our variability. Why don't we instead reward 10 shifts in a row that are between X and Y sort of tons or whatever, or some consistency and so on instead. I think of Jim Collins in his book, sort of Great by Choice, and he talks about Amundsen and Amundsen's venture to the South Pole. And Amundsen worked on a process of what was called a 10-mile march. So they marched 10 miles every day, regardless of the weather, regardless of other circumstances. Basically, it was a 10-mile march will get us there. And so maybe in the mining industry, we need to start thinking on a 10-mile march basis, and we need to start working on consistency rather than celebrating one-off peaks. There is certainly an approach in the mining industry of getting back on plan at all costs, shortcuts, inefficiencies, whatever that is. We said we were going to do this. We need to do this. We need to live up to our word. So therefore, we need to get back on plan. Those approaches to getting back on plan ultimately cost us at some point in time further down the track. Those inefficiencies or those shortcuts that we've taken will ultimately cause us greater pain somewhere at some point in time. And all they do, again, as I've said, is that they just increase the variability that occurs within a mine site. And then the mining industry is full of KPIs that drive silo effects. And so we have KPIs for the production department, and we have KPIs for the maintenance department and the process department and so on. And they're all about each of those individual silos sort of working to their best and theoretically sort of doing what is best for the mine overall. But in my experience, rarely actually sort of focusing on a team effort and consistency instead. And so they drive variability. But not only that, even within each of those departments, within the production department, you'll have the drilling team who have a set of KPIs and the blasting team who have a different set of KPIs and the waste removal team who have another set and so on. So you get silo effects and KPIs that drive behavior that increases variability even within the one department. And I think for me that the perfect example of this that I love to think about is the whole just-in-time and lean manufacturing process, which I think of as a sort of a fad of the 90s to some extent. I remember back in the 90s working at mine sites, and this whole just-in-time, we should run mines on a just-in-time basis, the same as factories run. We should carry far less inventory, etc. And we need to set up these systematic processes of cells, etc., that work to a drum beat every time. I actually think that shows our complete lack of ignorance of the variability that occurs within the mining industry, and that it is really chalk and cheese compared with the variability that occurs within a manufacturing process. And so I think that whole movement towards trying to introduce just-in-time, etc., again, just displays the lack of ignorance. So we really need to change the narrative. I think that we need to stop talking in fixed dates, and instead we need to talk in ranges. And so if I use that example below, instead of blasting finishing on day 15, which is our sort of, our mean deterministic plan for it, we should be talking that there's a 50% likelihood that blasting is going to finish between day 12 and day 18. There's a range around those results, or instead of the fact that the excavator is going to start digging on day 20, there's a 12% probability that the excavator will actually be ready to dig before day 15, before the sort of the mean of when the blast is going to be fired and so on. Well, let's talk in risk. There's a 27% risk that excavation is going to be delayed in this sort of example and so on. So, for me, it's like we really need to move to a totally different change in discussion of what we currently do. Let's start with understanding variability. So, we have, as I say, typically 6 or 7 sort of steps in a sequence in a mine, and we don't even know the variability across each of those different tasks. So we don't know which of those tasks has the greatest variability or the level of difference in variability between the 6 or 7 of them. Some of them will have a high degree of variability and some of them will have a low degree of variability. We don't understand the impacts on our schedule of the variability in any one of those 6 or 7 steps in the sequence. And we don't even know where we should start concentrating our efforts. If we were going to tackle variability and do something about it, where do we start? So if we understand variability, then we can talk about and we can start the process of managing variability. And we can also, if we understand variability, we can understand the impact of variability and therefore whether it is worth doing something about. And so if I take this simple example of mining waste and mining coal, and in this case here, the standard deviation for the waste is 4 days, while for coal it's 2.4 days. In this case, there's a 20.6% chance of an overlap between those two tasks, and therefore an issue. We have to do something different at the mine, sort of, and so on. But if we did something about variability and we could reduce the variability by 30% in this very simple example, and so our standard deviations went down to 2.8 and 1.7 instead, we've gone from a 20.6% chance of an overlap to a 12.5% chance instead. And so a 30% reduction in variability has resulted in a 40% reduction in risk. And for me, mine planning is actually, it's not just about a plan to achieve targets and so on, but it is actually about managing risk. And so that risk, a large component of that risk comes in through variability. And so if we're going to manage risk, then we actually have to manage variability. We need to change the culture, and this comes back to the optimistic mine plans. The purpose of mine plans is not to increase productivity. The purpose of mine plans is for execution purposes, for decision-making purposes, and for information purposes, depending on the length of the mine plan, from a shift plan through to a life of mine plan. Then they have a different purpose, from execution through to sort of information purposes and so on. And so optimistic mine plans lead to poor and incorrect decisions. It's a simple fact. That is a simple fact. And they can't be executed. They will reach the point where they're too far out and they're of no use. So it's really time to separate benchmarking from mine planning. Mine plans should not be used to increase productivity. That's what benchmarking should be for. So, benchmarking is for use in that continuous improvement process. And so when we want to start comparing production levels and how are we going, how are we trending over time, etc., we need to be comparing those back against the benchmark. And then then it can be benchmarks with stretch built into them and so on, but it's not comparing back against a mine plan with stretch built into it, because mine planning is for use in running efficient and effective mining operations. And the simple fact of the matter is you can't run an efficient and effective mining operation with a mine plan that is wrong. So today I've spoken about just 3 of the crimes that I've covered in my Crimes Against Mine Planning book. I've spoken about our unyielding faith in deterministic schedules and how we should be looking for 100% compliance to plan, holding people accountable to them, and we should be able to execute them exactly as is, for example. I've spoken about the complete lack of recognition of slippage that stems from dependencies, and the fact that our schedules will actually have slippage that we don't recognize because we're carrying out deterministic scheduling rather than probabilistic scheduling. Even the example with 5 days of buffer had a slippage of 6% in it. If all of our equipment out there was underproductive, under operating by 6%, that would be a significant focus. We would be having teams set up working out why our shovels are digging 6% less than what they're supposed to and so on. But we have this slippage that's occurring that we don't actually even know about. No one talks about it. It's not on the radar of anyone. And it's because we don't know about it in the first place, because we are still carrying out these deterministic schedules instead of carrying out probabilistic scheduling, which would then actually highlight the slippage and so on. And we would understand whether we need to address it and how big an issue it is. And then lastly, I've spoken about continuing to build in overly optimistic assumptions and the disease that I think that is, and how the fact is that you can't execute an optimistic plan. But that's really just the tip of the iceberg in terms of mine planning crimes. I've written about 10 in the book. I could have easily written about 20 or 30 I'm not necessarily planning to write mining planning crimes 11 to 20 because I really don't enjoy writing. It was enough of a strain to write the first book. So there's no plan for crimes 11 to 20 at the moment. But, in terms of the book, there are some other crimes that I cover in there that do actually have an impact on mine planning. I think that the three on the previous slide are the biggest issues, but there are other things such as we don't know how to execute a plan. We in executing a plan, we focus on the tasks themselves and how long they're going to take, whereas I think we actually should be focusing on the interactions. It's the interactivity between tasks, and it's the amount of float and lag that you have between tasks, and understanding as that lag is decreasing and you're getting to the point that you're going to have an interaction, and therefore your plan is going to be wrong and you're going to have to do something about it. That's what we should be focusing on in executing a plan. The mining industry is full of KPIs. However, it's rare that I see good KPIs that measure the quality of the plan. The one that I hear about the most is compliance to plan. That's not actually a measure of how good the plan is in the first place. That's a measure of how well we follow the plan. And so, how do we know if our mine planning is getting better over time? How do we know if mine planner A does a much better job than mine planner B? And then in actual fact, we need to do some training, coaching and mentoring with mine planner B to get them to the point that they're as good as mine planner A, for example. We can't do that without measures that measure the quality of the plan. We completely undervalue the importance of a good mine scheduling engineer. We rotate junior and inexperienced engineers through scheduling roles, which I think is a crime in the scheme of things. You shouldn't be scheduling a mine site unless you have done a lot of the other mining engineering roles first. And so therefore you have a good understanding of drilling and blasting and excavation and pit design, all those other sorts of things, so that you're producing a quality schedule rather than a schedule that's full of errors. We don't appreciate the role of enablers. So there are key steps in mining that we schedule, such as drilling, blasting, etc. But there are all these other things that enable those activities, such as drill bench preparation or ramp installation or sump excavation, etc., that enable those activities that we don't actually appreciate them in the first place. We don't schedule them and so on, and they invariably and commonly cause a problem in our scheduling. And lastly, we facilitate a culture of not following the plan. We talk about following the plan and so on all the time. However, a supervisor on a back shift or on the weekend or whatever it is can choose to do whatever they like and go off plan and so on. And there are no consequences for that. It's no big deal in the scheme of things. It's fine. The supervisor made that decision. So that is it